I'm not a machine learning person. I'm a modeler, so I do financial modeling and mathematical modeling applied to finance. My colleague Yudong Chen, he's a statistician and he's very experienced with stochastic blockchain models, and this is a work that we've been doing together. Now, Yudong is at the University of Wisconsin, and Xin is our former PhD student who is at Northwestern University. So so why did we do this? So a few years ago, financial contagion, so this means how shocks propagate through an economy that is modeled as a graph where we have connections between firms, was lacking algorithms to detect certain structures. So, and by structure, we mean underlying blocks of institutions that behave similarly. So there was a lot of research on modeling, like when you like belief propagation, if you have seen that. So how do beliefs propagate in a social graph? There were models that were quite similar, adapted to economic and financial networks, that were about how do you have a shock that comes from a cluster of institutions and then propagates to the others through economic linkages. And then, of course, the question, there was an assumption, inbuilt assumption, that certain institutions behave in a similar way, and so in other words, they behave as a cluster. But what we were lacking were algorithms that you could feed them the data and they could say, oh, these institutions are essentially behaving similarly as a cluster. Now, one of the problems that we were always facing in developing models for financial networks was that there isn't really just one financial network. There are multiple financial networks. Basically, any economic relation that you can think that one firm can impact another firm can lead to a potentially important network. So, for example, loans, like one firm has loaned to another firm, and that's and if one firm can no longer pay the other loan, that's one type of relation, and that can propagate, because if one firm cannot pay the loan to another one, then the other one cannot pay the loan to yet another institution, and so on. Other things that matter are these overlapping portfolios that I have on the slide. And overlapping portfolios means that institutions essentially invest in the same assets. So then if a shock happens and some of them have to sell on the market at distressed prices certain assets, then this is going to impact all other institutions and all other firms that hold similar assets, because the price is lower when we try to liquidate fast. And so there were this nature of different data for different type of networks, but at the same time, the algorithms that we could use were ad hoc, meaning that they were generic algorithms that were meant for any kind of networks, but they were not performing very well on these economic networks for various reasons. So detecting clusters is one of the biggest challenges in network science, and I have here generic clustering algorithms for those of you interested. And the main the textbook example, if you want, is modularity maximization, and this is something that is that is due to Newman 2006, and then there are other types of models like graph cut based models, and spectral clustering is one that is used very broadly, and hierarchical clustering. So all these are different methods that you could look up, and they are different generic methods. They're not for a specific type of economic, for a specific application. So Why not use one of these for financial network? Well, first of all, there is financial networks. They tend to be heterogeneous. That's not to say that other networks are not heterogeneous. So I would say that all networks that have this special structure, heterogeneity, are going to have a hard time applying off-the-shelf algorithms, algorithms that already exist and are broadly used. So there are interrelations across multiple subsectors and different inter and intra-connectivity. Now, the degrees of nodes, even those in the same cluster, may exhibit heavy tail distribution. So there are nodes that are in the same cluster, and also nodes that are not in the same cluster that have that can have high degree. So meaning that there are some firms that are connected to lots of other firms, and there are many firms that are not connected to that have low connectivity. So big ones and small ones, and by big means not necessarily size, but interconnection. There are also outliers, so nodes that are not necessarily coming from a specific sector or from a specific type of firm, but rather exhibiting different functions. So it could be once it could act like a large insurer, once it could act like a big financial firm that sells certain products, once like a big investor. So kind of a big firm that tends to behave like has different functions in the economy, and that could be an outlier. So in the United States there was an outlier like AIG Financial Products, and AIG was a big insurer initially, but it was also behaving in the financial crisis like a big bank or big investment bank that was selling some sophisticated investment products. So it was performing essentially a different function. So in some sense, when you get this in a network, you don't know, is it belonging to the cluster of insurers, or is it belonging to the cluster of investment banks? So you don't know. It's somebody that kind of plays different roles. And in the context of a machine learning algorithm, you could call that as an adversary, because it could mimic different roles. So I have a question: how do you define the connection in a graph of financial institutions? That's a very good question. As I was saying, a connection is broadly defined and is quite an abstract concept, or rather not abstract, but something that you could the good word is generic, and you could have, depending on your application and what kind of relations you are interested, you could define that this is a connection. For example, as I was saying, you could say that institution A has loaned to another institution B, and then this is a connection. The connection would be an edge in the graph, and then the size of that loan could be the weight of that on that edge. So this is one type of connection, but there are other types of connection. For instance, portfolio overlap. For instance, you hold a certain currency. Let's say that two firms hold the same currency that is not that's not one of the main currencies. So maybe and then it is exposed to the risk of that economy, for example. So then so then they are related to each other. There's a connection between them through these common holdings, that the fact that they hold the same currency. But on the other hand, it's like depending on your application and what do you want to do with the model, you say, maybe I don't care about the loans because the loans are not relevant to me. I care about common currency holdings. That's what I care about. So then you model those ones and you concentrate on that specific network. If you cared about the loans, then you model another network. And if both are relevant, then you have to, then it's more complicated because you have multi networks. So both are relevant. So really you will focus on depending on your application. Now, what we are going to be doing in this paper is semi-definite programming relaxation of the modularity maximization approach, and this is based on two existing papers in the literature, stochastic block model with outliers and degree corrected stochastic block model. So the stochastic block model is a model in which there is a certain connectivity between nodes in the same cluster, so the called intra-cluster connectivity, and another connectivity that is among nodes that belong to different clusters. And that's so you say that the cluster connections are more dense, like in a group of people that know each other, they connect to each other. That's kind of like let's say all the undergraduate students in one department. Then that would be a cluster, and then there would be another cluster, for example, another university that is maybe studying literature, and then they would be very connected with each other. So let's say humanities institutions, and then this would be they would also be connected to each other, and then the interactions maybe are not as strong between those two groups as they are within the groups. And not to say that there's no interaction, but it's just to say that the density of those connections is not as large. Or let's say one city and another city, the university students, and so on. And so, how do you decide which one are the clusters based on what you observed in terms of connections? Well, the clustering problem is originally an NP-hard combinatorial problem, where you want to say that each node you want to see which combination of nodes put into different groups is going to minimize is going to maximize modularity. And so, but if you like to look at all possible combinations and decide which one maximizes the modularity, then that is an NP-hard problem. So people have done what is called a relaxation of that. So that's instead of I will show you in a second. So this one is what we do in this paper. We have some guarantees for the recovery of the inliers, and then there are conditions for exact recovery, meaning that we would be able to say which one are the inliers, so which one are the groups, and of course the limitation is that the outliers are going to be so we wouldn't be able to identify the outlier with this algorithm, but this is normal for this type of algorithms. So there are several challenges in this work that is the heterogeneity, the fact that the degree distribution is heavy-tailed, and then also there are the proofs that we have used from the previous literature. They could have they were less challenging because they could look at aggregate contributions from the node, whereas we have to look at very carefully at the contribution in those necessary bounds from the nodes that and as a function of their degrees. And what we have also is the definiteness of the adjacency matrix becomes worse than in the previous works. So let me show you the model. So what you're having here is a graph. So the set of nodes is V, and the set of edges is A, and then you have N that are inliers. So those inliers means that they are the ones that belong to the community, and the outliers, they are the ones that don't perform a given function, but they could they could be connected to nodes in different communities. And so the inliers, they are partitioned into unknown clusters C1, C2, CR, and then you have the adjacency matrix. And the inliers, call them I and J, they are connected by an undirected edge with a certain probability. The probability is theta I, theta J, and then there's another probability given by the matrix B. So this BAB, that is called the connectivity matrix of the cluster. So this one tells a basic connectivity structure between the different clusters. So that's maybe this is a moment to stop and see if there are any questions on this. So any questions on this graph, on this on the slide? Okay, so then this is important. So this is I and J, they are connected by an undirected edge, but all you know is that there is a certain probabilities, and there is a probability that depends on theta I, theta J. So theta I and theta J are some weights that are assigned to the node I and J. That is, and this is independently of all others. If you had homogeneity, then all theta i's would be the same, so you wouldn't be having this. So in a graph that is not that does not have heterogeneity, you would not have a dependence on theta. You'd have only BAB, and BAB is the basic structure that tells you within a certain graph. You for example, if they would be all in the graph in the cluster A, then the connectivity. Then the connectivity is then the connectivities are BAB. So if you didn't have these weights, but because of these weights, then even edges between two nodes in the same cluster are going to be weighted by those quantities theta I and theta J, which means that theta I and theta J would give a relative ranking of the size of those nodes in the cluster. So we have some questions. So the concept of being inlier or outlier is not clear. So the inlier are the ones that adhere to this structure. So the inlier, they are members of community that behave according to this model. So they connect, they respect the rules. So those are the ones that respect the rules. So in what does it mean to respect the rules? They connect to other nodes according to this rule, according to these probabilities, theta I, theta J, BAB. So those are the inlier. Whereas the outlier, they are nodes that can have any structure, but they have connections, but you basically don't know what are the rules according to which they connect to other nodes. So they don't belong to a certain community, so they don't connect to other nodes according to this rule of connection theta I, theta J, BAB. So that would be the difference between an inlier and an outlier. So you couldn't say that an outlier belongs to a certain community. However, and this is exactly why this is exactly the point. You are going to be able to say which are the communities rather than saying which one is for sure an outlier. So you can't say that somebody is for sure an outlier, but rather who is likely to be an inlier. That is what this algorithm is going to do. So right. So are we going to find inliers only after running the model? Yes, indeed. So the ones that are, you are going to be given an adjacency matrix. So you're going to just be giving a snapshot of the network, and then the algorithm is going to tell you this is the cluster. And you in that cluster, there will be the inliers, but there could be also some outliers that are assigned to the to that specific cluster. But that's also that's okay. That's okay. The difficulty with the outliers is that they don't necessarily respect this rule, so you can't be sure that they connect to the other ones, to the other nodes according to the probabilities theta I, theta j, BAB. So they just can connect randomly. Okay, so let's move forward. And so you have an adjacency matrix that this is what you are being given, and so I will not go over this this notation. There's a lot of notation over here, and what you want is to so what your goal is that given a single realization of the graph, or there's going to be a random graph, so you're going to just see the adjacency matrix. Our goal is to recover the cluster. So you want to recover the cluster, and you want to obtain a partition matrix in the form of 2, 2. So you want to have a partition matrix that says to you that these nodes over here. So you want to say that so this J is an all one matrix. So this J says, so L1, L2, LR, those would be the sizes of the clusters. And here L1, this is going to be saying that the nodes, so the nodes that belong to that, so the nodes 1 to L1, they are belonging to the first cluster, and then they are connected to each other. So they are not connected to each other, they belong to the same cluster. So then you have xij is equal to 1 if and only if nodes I and j are assigned to the same cluster. And then you would like to find a partition matrix that says on the first nodes 1 to L1, they belong to the first cluster. So I'm going to assign there a diagonal block, all ones J L1. Then the nodes from L1 plus 1 up to L2, they belong to the second cluster. So those nodes are going to, you're going to have X, so you're going to have the all one matrix on the diagonal as well, and so on, and this is going to specify that those nodes belong to belong to cluster L1, L2, or LR. And yes, is there an overlap between cluster? That's a very good question. So we assume that there is no overlap between clusters. So but in general, of course, there would be an overlap in cluster. But for example, algorithms that would deal with overlaps between clusters, I think they are still being developed. So in reality, I would say that we would need algorithms that are able to deal with overlaps, but this particular algorithm does not deal with overlaps. So in our model, no, but in reality, yes. So for those who are seeing this modularity maximization methods for the first time, I think it is worth to go over the formulation of that. So in 2006, Newman defined the modularity as the link density within the cluster. So this is what you observe, minus the expected link density if degrees were kept constant, but edges were chosen randomly. So capital L is the total number of edges, and then if you look there at the sum, what you are doing is when you're summing up Aij multiplied by Xij, you are going to be summing the number of links that are between the nodes assigned in the same cluster. So if the matrix, and this is the matrix, this is the unknown. So the matrix Xij is the unknown that we are. So we are trying to, the algorithm is trying to find this matrix, and this matrix is telling us which nodes are together in the same cluster. So Xij is the matrix that is telling us which which nodes belong together. It's this block diagonal matrix that has all ones on the diagonals, and those correspond to the nodes that are in the same cluster. So if you sum Aij times Xij, then you're going to be summing adjacency matrix, so that is 1 or 0 if there's a edge present or not, times Xij, you're having 1 if I and j are in the same cluster. So this means that when you sum those over all nodes, then you're summing up all the nodes that are in the same, all the edges that belong to nodes in the same cluster. And then Dij, if you multiply that by Xij, then this is going to be the expected density if edges were chosen randomly, and then you choose them according to the degree. And you'd assign to each node a weight, and that weight would be the dj, so the degree, divided by the total number of linkages in the network, and that would be the expectation of the link density. And and then if in modularity maximization, what is the unknown? The unknown is Xij, so the entire matrix that gives the clustering. So in the literature, the tuning parameter lambda has been used to govern the relation between the weight of the missing links and those existing links. So the existing links again are the Aij, and the missing links are the ones that are so you're looking at what is there, Aij times Xij, and what should be there, that should be the this expected link density, and the gap between that those would be the missing links. So then you could look at the formulation 3.1, and you're trying to minimize that, so it is perfectly equivalent to maximize modularity, to minimizing that formula in that scalar product in equation 3.1, and this is subject to X being a partition matrix, and X being a partition matrix simply says that X writes in this block diagonal form, and those would be all ones. Now you can imagine that the convex relaxation of that would be saying, okay, I don't care that those are all ones, all I want is a convex relaxation. So you're going to be saying that instead of X being this block diagonal matrix with having all ones, matrices of all ones on the diagonal that have the given sizes, now you're going to allow X to be a positive semi-definite, and X having real values between 0 and 1. So those would be that is the relaxation. And then there are several penalties that are so what you have there, lambda. So the first scalar product there, this is the classical relaxation of modularity maximization problem. And then there are certain ways to deal with heterogeneity and with outliers. So in order to deal with the heterogeneity, one would impose a diagonal term, that is you would impose a diagonal term that would be alpha, and in contrast to what, so I think I'm going a little bit too fast on that. So the diagonal term here is going to deal with outliers. So that would be an alpha I, that would be a constant alpha on the diagonal. And if in addition you want to deal also with heterogeneity, we have to take into account the fact that each node on the has a different degree. So instead of looking at penalizing with a constant factor on the diagonal, so adding this term, alpha I, you want to add a term, and I'll show you in the next slide. You want to add the term alpha diagonal d star. So that would control the strengths of the diagonal penalization, and you'd have that each so the nodes would be penalized. So penalized means that we had this criterion in the optimization problem, in the minimization problem over X, and we penalize each node differently with the weight that depends on their degree. So nodes with high degree who do not belong to any cluster, then you're going to have that the degree penalty term dominates, and the nodes that have strong community membership, so the ones that we assume that that are inliers and they belong to a certain community, then for them the expected community links dominate. So now that you are asking this question, how do we determine that somebody is an outlier or somebody is an inlier, then I think that this would be a good criterion after the problem is solved, after the minimization is the minimization problem is solved, we will obtain a certain matrix X that tells us who belongs to which cluster. And then we can see, okay, in this minimization problem, you have this scalar product, and if the scalar product of X and alpha diagonal this star is dominating the other part of the scalar product, which is X, and this other part, lambda d transpose minus 8, which is the part coming from the modularity maximization problem. So if the diagonal penalization dominates, then this means that those nodes for whom the diagonal penalization dominates, those would be considered as outlier. We can consider them as outliers, whereas the other ones we can consider as inliers, because the outliers would be, okay, they may have high degree, but they don't have this big community structure. They didn't connect in the graph according to those rules. They didn't connect according to the theta I B and multiplied by the matrix B, that is the connectivity matrix. So the ones that are the outliers, the first term would dominate, and this would be a way to detect them. And so that'll be the algorithm who is going to say this. That's not to say that the algorithm is not going to assign them. The algorithm is still going to assign them to a graph, but in practice we can consider that they are outlier. However, the algorithm is not going to give the guarantee that they are outliers. So it's never going to be guaranteed. The algorithm is going to give a guarantee about the recovery of the inliers. The other ones we can make some assumption that they would be outliers, but the algorithm doesn't give, because it's very hard to define that somebody is an outlier. It's difficult to say, okay, these are the outliers. Okay, so now about the theoretical guarantees, I will just parse through them because I want to show just what kind of results are there. So mathematically, the results depend on some, so they are, what they are intervals for some tuning parameters, and the tuning parameters are those ones. So the tuning parameters are alpha and lambda. So this you would choose heuristic. One would use heuristics to tune them, and now the theoretical guarantees are saying, okay, if those tuning parameters lie in certain intervals that depend on some quantities that are based on the true clusters, then we guarantee to have perfect clustering. So as you can see, it's both art and science, because the science gives this theoretical results, but then there's all the art of choosing the tuning parameters so that they are within those ranges. And the theorem for perfect recovery says, okay, if lambda, the tuning parameter, lies within this range in equation 4.2, if alpha, the tuning parameter, is larger than this other quantity in 4.4, then you are able to recover the clusters. So with a certain probability that is that asymptotically goes to 1, so you can see that it goes to 1 with 1 over n, then the solution will be in the form that we desire. So it is going to have this block diagonal structure, and when it has this block diagonal structure, we are going to be able to find the cluster. So from this block diagonal, we can find the clusters, and so then going back to this was the science, and then the art is you of course you will choose them in practice according to heuristics. So this is what we used in our in the way we implemented the algorithm. So we chose that d is equal to 1. So we didn't this one d is equal to 1 basically means that when we use the penalty on the diagonal, we penalize the degree. So we didn't cap this degree. We took the degree itself. Lambda is we use the tuning parameter lambda as in the classical modularity maximization problem. If you recall, the classical maximization problem, lambda was equal to 1 over L, and where L was the number of edges. So and then what we said is that okay, we can instead of using 1 over L, we can use a tuning parameter. Well, in the implementation, that is exactly what we do, and we show that the results are robust to scaling the parameters. And so then this usual parameter choice of parameters work in practice. So they satisfy those conditions in the theoretical guarantees. So what we did is apply this algorithm to finance. And I want to emphasize that, of course, this is not just one application. We can have other applications as well. So this is we were motivated by the finance example, but one can think about, so what we need for this modularity maximization are networks that are mid-size. So financial networks are kind of having 2,000 nodes and a certain number of clusters. So if you recall, you know the number of clusters, you can have something like 6 clusters, things like that. So if you have a network that is heterogeneous, that has maybe some outliers, some nodes that are not necessarily in one specific group, but can perform different functions. So I guess that this relates to the question about overlapping clusters. You could think about, for this purpose, that these outliers could belong to different clusters, not commit to one of them, so they could be part of the overlap. Well, so if you have other examples of such networks, and I guess that these methods would apply. Of course, you need to test them against the ground truth. So you would need to test how the clustering performs for your specific application. So this is what we did with this finance. So we had some samples from the Korean network, 20 samples. So we did semi-synthetic networks. So we don't have the exact networks, but we know certain things about those networks. So we know, for example, the aggregate size of assets and liabilities, and we know the ground truth because we know which sectors we have in. So we know each node. Does it belong to insurance? Does it belong to banking sector? Does it belong to mutual funds? Does it belong to I think those are some of the main ones. So you have them here. So bank, insurance, credit, specialized finance, asset management, mutual credit cooperative, and securities companies. And then here, this is what we actually had from the data. You have sizes, and this. And of course, we have multiple banks, and within each group of banks, it is exactly the kind of setup that we have because each one has a different size. So we use that for the quantity theta, and this would provide, if you recall, this matrix B, this basic matrix that gives the probability of connection between different clusters and intra-clusters. So that would be the basis of our matrix B. Right. So we use this, and we created certain networks. So this is how it looks: a semi-synthetic Korean network with blocks of nodes ordered as follows. So banks would be the first 17 nodes, and insurance company next 41 nodes. And what you observe there on the top is that you can't really. So if you look, so visually, it looks as the first block that are banks and insurance companies are one big block, right? It looks like a block diagonal, a big block diagonal. But if you look carefully, the connection pattern is different, because you see that the banks, which are only the first 17. So unfortunately, I can't really plot. I can only do the slides backs and forwards. You can't really see my pointer. But if you look at the first 17, they tend to connect to all of them. So you have this kind of rows. You have a connection on the top rows and on the first columns, right? Whereas the next block, which are the insurance, they don't have this type of connection. So the algorithm should be able to detect that the first 17 are a different block than the next 41. So then what we test is we test several algorithms, and we want to see what is the misclassification rate. And our algorithm has for most of this network has a lower misclassification rate than the standard algorithms. Other application that we did was about overlapping portfolio. So this would be for investment portfolio management. So now, why would you want to do that? Like, say that you have a portfolio, and then you want to diversify. So you want to diversify. You want to see which one are behaving similarly. So those would be a cluster, and which one are behaving differently from the first cluster, but similarly to each other, so that you put equal weights on those two clusters, let's say, and you don't put all your money on one cluster, because that would be a very undiversified portfolio, basically. So this is something that is used. So we looked into that problem, and this is an example where the network is something that we created ourselves. We said, well, you have these funds, and from their data series and from their holdings, I can infer what is the connection between them, and then I can run a clustering algorithm on that. So as you can see, we use the connectivity matrix according to the holdings in different assets. So for example, I gave the example with currency. So currency holdings, let's say in 2003 versus currency holdings in 2012, and those would be somewhat how the clustering looks like. So this is a recovered clustering, and one can see that, and again, there is no good way to say that the clustering is correct, because here we don't have the ground truth. But what you could say is whether your clustering has desirable properties. Is it like, can you see very well the block diagonal structure, and does it behave in a reasonable way? So you see that from 2003 and 2012, there's the bigger cluster is more important.